Well, welcome again to Maths 315, and this is the third video in Chapter 3 on series and summation. And I'm going to begin, I hope you're not too overpowered by this, but I'm going to begin with quite a difficult example. You're not expected to be able to reproduce any of this, but it is an important example and one I wanted to include. Ideas like this and questions like this have in fact appeared in the HSC papers in the past, and so the maths is not too difficult, but it is very interesting limit we're going to look at. So we've already seen that if I put my finger over this for the minute, then this is the partial sums of the harmonic series, which we know diverges. And so I know that this limit doesn't exist. This limit goes off to infinity. However, it was realized several hundred years ago that if you take the partial sums up to n of 1 over k and then you subtract off log of capital N, so you get the partial sums minus log n, and then you take a limit as capital N becomes very big, then this limit does exist, and it's a very mysterious object. It was studied by Euler and others, and is still, we don't really completely understand this limit today. What I'm going to do here is I'm going to use some geometrical ideas to prove that this limit exists. So I'm going to take the partial sums. So I'm going to take the sum of the harmonic series up to 1 over n, and then subtract off log n. And we're going to study this particular sequence now of partial sums. So I'm going to look at the difference between two successive terms of this sequence. So I'm going to replace n with n plus 1 and then subtract off a n. So all of this bit will disappear, and I'll just get 1 over n plus 1. That's the next term along we get from here. I'm replacing n with n plus 1, so I get minus log n plus 1. Then I'm subtracting off an, so I'm going to get plus log n. And I want to analyze this quantity here and see what it is, see how big it is. And we do that by looking at some geometry and looking at some areas. So we're going to take the curve f of x is 1 over x, y equals 1 over x, and I'm going to look at it between n, which is an integer, and n plus 1. Now observe then that the area of this, I'm going to draw a little under rectangle here. So this shaded area has got width 1, and its height is 1 over n plus 1, because our function's 1 over x. So the area, this shaded area then, is just of area 1 over n plus 1. Now it's pretty clear that this shaded area is less than the area under the curve between n and n plus 1, which is given by the integral. So this rectangle, the area of this is less than the integral of 1 over x from n up to n plus 1, and that's a standard integral. It integrates out to log, put in the endpoints and subtract. Now I'm just going to rearrange this inequality here, so I'm going to leave that there and take these terms onto the other side. So when I take it onto the other side, it becomes minus log n plus 1, and the minus log n on the other side becomes plus log n. So I take all these onto the other side, and this is then less than 0, i.e. this thing is negative. Now of course this quantity here was exactly what we got up here when we worked out the difference between successive terms. We got the same expression. So that tells me that an plus 1 minus an is less than 0, and that means that an plus 1 is less than an. That tells me that this sequence of these partial sums is a decreasing sequence. Each term is less than the term before it, so the values of this are getting smaller. This is a decreasing sequence. Well, I want to now show that is in fact bounded below. So, to do that again, I'm going to use some geometry. I'm going to use that same curve, f of x is 1 over x. Here it is. And I'm going to draw the numbers, the integers from 1, 2, 3, and so on up to n. and I'm going to draw some rectangles. Forget about the first column for the moment, just look at this bit here. So I'm going to draw some rectangles. So I'm going to get a little shaded area that's between these lines and the curve, and I'm going to get a rectangle here. Now the area of this rectangle is going to be the base, which is 1, times the height. This is the function 1 over x, so 1 over 2 is a half, half times 1 is a half. The area of this rectangle similarly is 1 times 1 over 3, so that's a third, and so on all the way through to 1 over n. Now these shaded areas, I'm going to push these across into this first column. So all I'm doing is I'm just essentially copying that into here and shifting it across to there. I copy that from there, shift it across to there, all the way through, and then this last little bit gets shifted across to there. Now this rectangle here, right in this first column, it's got width 1, and it's got height of 1, because the function is 1 over 1, so 1 times 1, which is 1. So the area of this whole rectangle here is just 1. In fact, it's a square. And you can see by the way I've constructed this that the sum of all these shaded areas in here that I got by pushing all these areas across, this is going to be less than the area of the first rectangle here. Well, now all I'm going to do now is to write down what we've done more formally. So this shaded area here is going to be the area under the curve, that is the whole of this. That's the area under 1 over x from 1 up to 2, minus the area of the rectangle, minus a half. This little area in here is going to be the whole area under the curve between 2 and 3, minus the area of the rectangle, which is a third. And I continue this all the way along. It's going to be the integral from n minus 1 up to n, 1 over x dx, minus the area there, which is 1 over n. Well, I can now add up all these integrals. This is the integral from 1 to 2, 2 to 3, 3 to 4, and so on up to n. So I can combine all those together as just the area under the curve from 1 up to n of 1 over x dx. Minus, I simply now add in, I've got my half, a third, and so on up to there. I can bracket those together. And whatever this is, this area is the sum of all of these shaded regions, which is the sum of all these shaded regions, and as we saw, that's less than 1. And I can rearrange this now. I can integrate this. I get log n, and I can take all of these terms onto the other side and then read the thing backwards. So I'm going to get 1 plus a half plus a third and so on up to n, 1 over n, and then minus log n, and all that's bigger than 0. That tells me then this partial sums, because this now is just the partial sums, this is now bigger than 0. So our sequence is decreasing, and it's bounded below by 0. And again, we can invoke the monotone convergence theorem, and we can now conclude that this an has a limit. In other words, that means that this series up here converges. Now, what does it converge to? Well, you can get an approximate value of it as a decimal. It's got a special name, this limit. It's written as gamma, and it's often called Euler's constant or the Euler-Mascheroni constant. And you might like to Google that if you want to find out more information about this mysterious gamma. It's approximately 0.5772, etc. But we don't know very much about it. It's a great mystery. We don't even know whether it's irrational or not. Surely it is, but we have no proof of that. It's a very interesting number, and what's surprising is that this number turns up in all sorts of weird and wonderful places in mathematics where you would least expect it. In particular, in problems analysing the distribution of prime numbers, which is a great mystery. Okay, well, that was a hard example. I hope you could at least follow through. Not expected to be able to reproduce it. I hope you could at least follow through some of the steps there. And some of the techniques we use there about comparing areas is a very useful idea in mathematics and in analysis. So I'm going to now develop some tools which will enable us to analyse the convergence of series. So firstly, this next theorem says if you've got a series of non-negative terms, that is, all these are either zero or positive, then this infinite series converges if and only if the sequence of partial sums is bounded. Now, I've left the proof of that to one of the harder problems in the tutorial, but this again is going to follow from the monotone convergence theorem. Now, using this, we can state and prove the following fundamental tests. This is really important for convergence. And this is our theorem 4.4. And this is the one you need to get your head around, because we're going to use the comparison test quite a lot. So I've got two infinite series with non-negative terms, and I'm going to assume that this ANs are always behind the BNs. So I like to draw a little picture here. So there's the AN. For every n, there's AN and there's BN. So AN is always on the left of BN. Now, if the infinite sum of all the BNs converges, then the infinite sum of all the ANs should be less than that. So in other words, this is a finite number. The sum of all the BNs is a finite number. This theorem says, well, then that makes the sum of all the ANs a finite number, because it's going to be on the left of the BNs. On the other hand, if the sum of the ANs diverges, that is, if the sum of the ANs goes off to infinity, the BNs are bigger than that, so they're going to go off to infinity as well. So do the BNs. Now this is called the comparison test. And what the way we're going to use it is, we're going to, given some infinite series, we want to show it converges, for example. Then what we're going to do is we're going to show that our series, our ANs, are less than the BNs. We're going to show that the sigma BNs converge, and that will force the ANs to converge. Anyway, you'll see when I do some examples how it works. There's just a little quick proof of this here. We let capital S of n and capital T of n be the partial sums for each of these two infinite series. Now the AIs are bigger than less than the BIs for every I, and that means this sum is less than this sum. So the partial sums of the ANs are less than the partial sums of the BNs. Now the sigma BNs converge, and by our earlier theorem 4.3, that means the partial sums are bounded. That means the TNs are less than some L, for some L in R, and that tells me there the SNs are bounded. The sequence is of positive terms, so it's monotonic increasing, and that says that converges by the monotone convergence theorem again. Part B is done exactly the same way. Now the comparison test is the basic test I'm going to use for all series, really, although we will develop a couple of other tests, but all of them rest ultimately on this comparison test. Now if we're going to make a comparison, we've got to have something to compare things with. So when we're using the comparison test, we're going to often compare a given series to this series, sigma 1 over n to the power p. This also itself is a very, very interesting infinite series, and I'm going to call this a p-series. And we're going to have then this p-series test. We'd like to know for what values of p does this converge. We've already seen if p is 1, this is the harmonic series and it diverges. And we saw if p was 2, that was the Euler series that converged. Well, what about other values of p? Well, theorem 5.4 tells us exactly what's going on. So the series sigma 1 over n to the p converges if p is strictly bigger than 1. If p is equal to 1 or less than 1, then the series diverges. Now that's a really important fact, so that's something you have to learn carefully. Sigma 1 over n to the p converges if the p is bigger than 1, and diverges if p is less or equal to 1. The proof of this is very similar to what we did when we looked at the Euler sum, so I'm not going to go through that here. Now, the best way of seeing how this works is to do lots of examples. So I'm going to do 4 examples of this, and then we'll have some more in the tutorial problems. So these are the sort of things I expect you to be able to do. So I give you this infinite series, 1 over n cubed plus 1. We want to test this for convergence. So here's how we approach this one. Okay, so when I first look at this, I do much the same as I did when we were talking about sequences right at the beginning. I look to see where the dominant term is. If I offer you $1 million cubed or $1 million cubed plus 1, well, it's the $1 million cube that grabs your attention, not the plus $1. Who cares? So roughly speaking, it doesn't equal it, but roughly speaking, this is 1 on n cubed. So this is like our p series with p equals 3. And we know that that one converges. So that's what I do in my head before I write anything down. I work out what do I think this is going to be doing. The plus 1's not important. This is a p series for p equals 3. We expect it to converge. So that means I want to get this less than something. If I want convergence, I want to get this series less than something. Well, what do I want to get it less than? I want to get it less than my first guess, this p series. And that's true because n cubed plus 1 is bigger than n cubed, so 1 over it is less than 1 on n cubed. Okay, so just note that step. We needed to get a less than sign here, and we get one automatically. The less than sign enables me to toss away the 1. Now this series here converges by our p-test with p equals 3. That's how we're going to set these out. So we're going to mention the p-test, and I want you to tell me what the value of p is. So this p is bigger than 1, and therefore this series converges. Therefore, the given series, the one we started off with, that converges by comparison. Now that's the way you'll set these out. That's the sort of language you use. You compare the given series with one of the p series, decide whether this converges or not. This one does because p is 3, and then we can conclude that the given series converges by comparison. And you've got to write out all the English here when you're doing these problems. Okay, second one, we're going to have a look at the sum. This was back on the sheet here. We're going to look at the sum n on the square root of n to the 6th plus 1. So here it is. Now what's going on inside my head again? Well, again, the plus 1 doesn't amount to much at all, so I'm going to pretend the 1 wasn't there. And if I look at I'm going to toss away the 1. So I'm going to write this as less than n on the square root of n to the 6th. Now the square root of n to the 6th is n cubed, and I can then cancel one of those and I just get n squared. And there's our Euler sum. So this infinite series is less than this infinite series. This one converges by the p-test with p is 2. As long as this number is bigger than 1, we have convergence. And that means the given series, the one we started with, this one here, converges by comparison. Converges by comparison. Now the third one, I want to do a few of these. This one is sigma n minus 2 on the square root of n to the 8th plus 1. So we do the same idea again. I take my infinite series here and I look at the dominant terms. On the top who cares about the minus 2? What we're interested in here is the n. Who cares about the plus 1? So I imagine putting my finger over these and just looking at this here. And so this will be n on the square root of n to the 8th, and that comes out to n cubed. So again, I'm going to compare it with my p series, and the p will be equal to 3. So here's the setting out. Firstly, there's the series we were given. We toss away the 2, n minus 2 is less than n, and we toss away the plus 1, n to the 8th plus 1 is bigger than n to the 8th, so in the denominator this is less than. Now I can simplify this. This is n to the 4th on the bottom, n on the top cancels to n cubed. Again, this is a p series, so this converges by the p test with p equals 3. And that means the given series, the one we started with, converges by comparison. Now, the obvious question to ask, if I just have a look at this again, you might say, well, hang on a minute, what if that was a plus 2 there and a minus 1? Then this inequality doesn't work anymore. And that's true. Now, there is a way of introducing some fractions and things and fiddling around. We can do that. I'm not going to torment you with that. It can be done. If that's a plus 2, then I can say n plus 2 is less than 2n. I can put a 2 in here, and then eventually the inequality will work. I'm not going to fiddle around with those things. I just want to make sure you understand the basic principles, so I'll always give you series that we don't have to do any fiddling around with adding in extra numbers and fractions to make the inequalities work. But that probably would have occurred to you when doing this problem. Okay, the last one, number D here, is these all converge so far. I wanted to do one which doesn't. So here's sigma n on the square root of n to the 4th minus 1. And here is the solution to this one. Now again, this time I'm going to, let's get rid of the 1 for the minute. So n on the square root of n to the 4th minus 1, it's roughly the same as, doesn't mean equal to, but roughly the same as, get rid of the minus 1, square root of n to the 4th is n squared, and this is 1 on n. And so by the p series, sigma 1 on n now is going to be our harmonic series, which we know diverges. So this time we want to get the inequality the other way. We want it bigger than something in order to use part B of the comparison test. So I'm going to say here n to the 4th minus 1 is less than n to the 4th, so in the denominator this is bigger than n to the 4th. We simplify this down, as we saw we get 1 over n, and this one diverges by the p test with p equals 1. This one is bigger than something which zips off to infinity, so that means the given series diverges by comparison. The given series diverges by comparison. So I'll leave you just to think about that for a second. And we're going to now introduce a second test. We're only going to have essentially 2 of these ones. There's the comparison test, and series involving exponentials on factorials. When you're dealing with a series with exponentials and factorials, the following test is very useful, and we're going to need that later on too when we get to power series. And this is called the ratio test. And this again should be learned very carefully, and you need to know how to use it. So the ratio test, we let an be a series of positive terms again, and we're going to look at the ratio of the n plus 1th term to the nth term. So I'm going to look at an plus 1 over an. We're going to take a limit of that as n becomes very big, and we'll get some number r, we hope. This in fact limit might not exist, but if it exists and it equals r, then the result says that this will converge if r is less than 1, and diverge if r is bigger than 1. By the way, if r equals 1, the test fails. It doesn't tell us anything. And there's a tutorial problem to show you there. 2 examples where r turns out to be 1. In one case, the series converges. In one case, the series diverges. So if r equals 1, the test fails. It doesn't tell us anything. Now just note here that r has to be bigger or equal to 0 because all the terms are positive. So when you work out this thing, whatever it is, it's got to be positive. So we only care then whether it's less than 1 or bigger than 1. Now I'll do one example of this here, show you how to apply this. It's a very easy test to apply, actually, a very nice test, and you'll use it when you've got factorials and exponentials and powers and things. Generally, I will tell you, use the ratio test to do something, so I'll tell you which test you've got to use when I ask you to do things on this. So here's the first one. So we're going to look at sigma 1 on n factorial. So it's 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial and so on. Assuming we start off at n equals 1, of course. So here's my an, it's 1 on n factorial. So we're going to look at an plus 1 over an, and we're going to look at the limit of what this does as n gets very big. So I just plug it in. So a sub n plus 1 is 1 on n plus 1 factorial divided by 1 over n factorial. Now, of course, when you're dividing two fractions, you invert and multiply. So I've got 1 over that one times n factorial over 1. When you simplify, you get n factorial on n plus 1 factorial. Now, n plus 1 factorial simply means n plus 1 multiplied by n and all the numbers below, so I can rewrite n plus 1 factorial as n plus 1 factorial by n factorial. These now cancel out, and I just get 1 over n plus 1. And that limit is easy. As n gets very big, 1 over very big is going to 0, and that's my r. Now, in this case, r is 0, and 0 is less than 1. And that tells me this series converges by the ratio test. This series converges by the ratio test. And I'll do a couple more examples of that in the next video, and we'll be looking also at alternating series.